Hello, this is Jared Bryan. I'm going to talk about something really important to thinking about earthquake geoscience, which is deformation. This is really a concept that unifies a lot of ideas in earthquake geoscience. So, anytime we want to talk about slip on faults that generate earthquakes, or the propagation of seismic waves through the earth, or the damage to buildings from seismic waves, or anytime that we see a fault or fold or fracture in the rocks, we talk about these things through deformation. But before talking about the way deformation shows up in earthquake geoscience, we should be a bit more precise about what we mean by deformation and the different ways an object can deform. So, by deformation, I mean some change in the shape or size of an object, call this strain, in response to some applied stress. So, for example, pushing on this cube from each of its faces causes the cube to compress, changing its size, whereas if you dragged it from the top, it would change its shape. And the exact way that these stresses are converted to strains is a property of both the particular material you're interested in and the way you exert the force on the object. You can think of lots of different examples of different ways that things deform. For example, when you put enough stress on glass, it shatters, whereas rubber squishes or stretches. So, before we can meaningfully discuss deformation, we need some way to describe the differences in the way materials respond to applied forces. One important classification we can make is the type of deformation. Some deformation is reversible, which is to say that it's temporary. You can deform the material, but when you release the force you're exerting on the object, it returns to its original shape. For example, you can consider a slingshot. You pull back on the pouch, extending the band. The band resists that extension, and it snaps back to its original shape when you release the pouch, which is what sends the projectile flying. Now, the tendency of the band to pull back to its original shape is an example of elasticity. Now, the slingshot is an obvious example, but in fact, most materials behave elastically when the forces on them are small enough, including rocks and building materials. One important way we can formalize this idea of elasticity mathematically is through Hooke's law, which says that the deformation of an elastic material is proportional to the force you apply to it. Hooke's law is given by the equation F equals negative kx, where F is the force you apply to the object, x is the amount the object deforms, and k is the stiffness of the object. This law says that if you double the amount of force on an object, it deforms twice as much. So you can think about Hooke's law as describing the extension of a spring holding different masses. The first spring is not holding any mass, so we say its extension is 0. If we add some mass, m, the spring extends some distance, delta x. And if we double the mass to 2m, the spring extends twice as far, to 2 delta x. We can describe this behavior with a graph of the force on the spring versus the amount of extension the spring undergoes. We find that the stiffness of the spring is just the slope of the line that the graph traces out. So this is something really important. We can measure the material properties of an object, in this case the stiffness of the spring, by applying different forces to it and seeing how it responds. But materials can behave in other ways too. Some deformation is irreversible or permanent. You can deform the object, and when you release the applied force, the object stays deformed. You can think of this like crushing an aluminum can. You apply some force, namely stomping on the can, and it deforms or crumples, and it does not spring back to its original shape. This is plastic deformation. Most objects are elastic at small forces, but eventually they're damaged beyond repair and start deforming plastically. So we can extend that force versus deformation graph from the previous slide to see that the deformation shows up as continued deformation, increased extension, at smaller and smaller increases in force. So the point where the material stops behaving elastically and starts behaving plastically is known as the elastic limit. And we can divide that graph into two, showing both the elastic and the plastic portions of the graph separated by that elastic limit. And if you keep putting force on that object, it can even break entirely. Think back to the example of the slingshot. If you stretch the band too far, it might be permanently stretched out, and if you keep pulling on it, it might even snap or fracture. On the force versus extension graph, this is represented by the red X. Now, one important thing to note is that pre-existing defects in a material can reduce their strength by a lot, even if the defect is small. This causes the material to fail at much lower stresses. So, an example of a pre-existing defect might be a fracture in a rock. That way, when you put forces on the rock, it's much more likely to fail along that pre-existing fracture. We've now seen that the amount of force applied to an object controls how the object deforms, but the type of deformation is also controlled by properties of the material itself. So first, why is it important that we understand material properties at all? Well, if you want to know when the rocks on a fault will break to generate an earthquake, you need to know how much stress they can support before breaking. If you want to build a building, you need to know under what conditions will the building fail. You wouldn't build a bridge out of glass, but you might build one out of concrete. And the reason you would do that is due to the material properties of glass and concrete. So, in order to quantify the difference between those material properties of glass and concrete, we use things like the stiffness, or the resistance to applied stresses, the strength, the stress a material can support elastically, hardness, which is the resistance to scratching or indentation, and many, many more material properties. So with that background out of the way, we can now go through the hard work of measuring material properties and observing deformation types in a real example. So in this first example, I'm creating two different springs from copper and steel by wrapping wire 15 times around a 2 centimeter rod. I then hang the spring from a hook and go through a similar exercise as in our discussion of Hooke's law. I add different masses to the end of the spring and measure how much the spring extends. I then plot these data points on a force versus extension graph. Here you can see my humble setup for measuring the stiffness of copper and steel springs. I have my homemade springs hooked onto a screw, and I'm adding water to my water bottle to change the mass on the spring. Pause the video now to dissect this graph for the two springs and answer a few questions. First question, at what masses do the springs reach their elastic limit? Feel free to go back to the slide on plasticity for a reminder about how to identify the elastic limit. Second question, does Hooke's law seem like a reasonable model for this data? Feel free to go back to our slide on Hooke's law for a reminder about what Hooke's law looks like on a force versus extension graph. Third question, where do the springs behave elastically and plastically? If you need a reminder, the slides on plasticity and elasticity will have what you're looking for. Okay, hopefully that went all right for you. I've now truncated the graph to show only the data points in the elastic region. This spoils questions 1 and 3 from last slide, so if you haven't yet answered those, close your eyes and go back to give them a try. On this graph, I've plotted the best fit line to the force versus extension graphs for the steel and copper springs, along with the equation of the best fit line and the goodness of fit R-squared metric, which just shows you that the lines fit very, very well. Pause the video here again and try to answer these two questions. Question 1. What is the spring constant of each spring? If you need a reminder about how to measure the spring constant, head back to the slide on Hooke's law. Question 2. Which spring is stiffer and how do you know? Keep in mind that the spring constant measures the stiffness of the spring. Ignore negative signs here for the time being. Great, so now we've measured a very important material property for two very important materials. We saw both elastic and plastic deformation in the spring at different forces. Now we'll repeat this exercise but with rubber bands of two different thicknesses with and without a pre-existing defect, which is given by a little snip in the side of the rubber band. As with the previous example with the spring, I'm hanging the rubber band from a hook, adding masses to the end of the rubber band and measuring the extension, and then plotting the results on a force versus extension graph. Here you can see an example of my rubber band with a pre-existing defect. We want to load this rubber band and compare the force at which it snaps with the force at which the undamaged rubber band will snap. And just a reminder that you don't need anything special to do this exercise. I'm adding water to a water bottle to increase the mass on the rubber band. Again, pause the video and dissect these graphs, which show a force versus extension plot for thick rubber bands with and without a defect, and for thin rubber bands with and without a defect.
Question 1. What is the fracture strength of each of the 4 rubber bands? That is to say, at what masses do each of the rubber bands break? Head back to our slide on fracture if you need a reminder on what this point is. Question 2. Does Hooke's law seem like a reasonable model for this data? Finally, pause the video and see if you could generalize some of these concepts I introduced in this video to examples from the real world and from geoscience. What are examples of elastic deformation, plastic deformation, and fracture from the real world?